Welcome to lesson 7. Today we will be working more with proportional reasoning and the constant of proportionality. You'll need to have out your math book and be on page 56. You'll need a pencil and a calculator for today's lesson. All right, let's get started. Our lesson today is all about comparing relationships, these proportional relationships, using tables to help guide the way. We're going to explore how proportional relationships are different from other relationships. And we're going to represent our information, as I said, on a table. And we'll be able to really tell if a situation is proportional or really is not proportional. As a warm-up, we're going to start with some dividing of fractions. We are going to start with the first problem, 3/4 divided by 3/7. And this is a review. And to divide fractions, you take your original fraction and you multiply it by the reciprocal of the other fraction. So we will do times 7/3. Now, I believe in cross simplifying, and as you can see, I have a 3 on the top and a 3 on the bottom. So I can say, all right, 3 divided by 3 is 1. 3 divided by 3 is 1. It just makes simplifying at the end much smoother. So I can take 1 times 7 and get 7. And I can take 4 times 1 and get 4. So my answer is 7/4. And I can also write that as a 1 3/4. Let's go on to our next problem. We're almost ready to go. I need to convert this to an improper fraction. And as we know, if we multiply and then we add, and we know that 2 times 1 is 2, plus 3 more is 3/2. I could draw an image where I know a whole is 2/2 as well, and then I have 1/2 more, comes up with 3/2. Divided by 2/3. And I know that I need to stay with my original fraction and multiply it by its reciprocal. So it becomes 3/2 times 3/2, which is 9/4. I multiply across. 3 times 3 is 9. 2 times 2 is 4. And I can rename that as 2 1/4. Because I know that 4 goes into 9 2 times, and I have a remainder of 1/4 left over. So let's get into today's lesson. The first activity is going to be visiting a state park, where we're going to have vans or vehicles of people, where each situation we get a cost of $6 a person, and then $2 per person going in. And here it says, what do you think the essential question it would be? And essentially, I really think, as we know, for going into a park, how much is it really going to cost us to get in? So what we've got here, and you'll notice you're on page 56, number 1 says, how much would it cost for a car with 2 people to enter the park, 4 people, 10 people. So this is just a table, just very similar to yours, that gets that information. Now, don't forget, we know that it's $2 per person plus $6 for the vehicle. So we're always paying that $6 before we even think about our number of people. So we know in this situation, we've got the $6 plus $2 for 2 people. And I wrote that as 2 times 2 because it's $2 per person. So we would write that as 6 plus the 2 times 2, which is 4, and that gets us 10. So it would cost $10 to get in with 2 people. Now let's figure it out for 4. Again, just like in the last situation, we've got to pay $6 before we can even figure out our costs per person. And we have $2 per person, but this time we have 4 people, and 2 times 4 is 8. So I really am doing 6 plus 8, and that's going to get $14 for 4 people to get in. 10 people, we're going to keep the same situation going, where we've got $6 that we have to pay plus $2 for 10 people. And that $2 for 10 people is that 2 times 10, which gives us 20. And then we have to add it to our 6, which gives us 26. So we just finished number 1, filling out the cost per person here. Now it says for each row on the table, if each person in the vehicle splits the entrance cost equally, how much will each person pay? Well, let's take a look. If we have the 2 car, 4 car, and 10. Oops. Let's just take a look at what this would be. So on the right here, it will be our price per person. So for the first car, I'm just going to type in we've spent $10 and we have to split it between 2 people. So I would do the 10 divided by the 2, which gives us $5 a person. So that's the cost that everyone pays if we have 2 people. Now, if we have 4, looking back at our table, the cost was $14. So if I'm going to split that between the 4 people, I would do the 14 divided by 4. Oh dear. 14 divided by 4. And that gets 3.5, and we know that's money, $3.50 per person if we have a car of 4. Now, if we've got a big old van with 10 people, well, we just calculated earlier that it would cost 26 to enter the park. So I'm going to divide the 26 by 10, and that gets 2.6. And because it's money, I'll add a 0 here, $2.60. So does that change depending on the number of people? Absolutely. What this is an example of is this problem does not have a constant of proportionality, because what we essentially just did is if we called this our x and our y, we did our y divided by our x and got $5. We did our y divided by our x, got $3.50. Our y divided by our x, and we got $2.60. It's not the same constant of proportionality throughout. So is there a way, number 3 says, can we determine what it would cost for 50 people? Well, just like with the pattern that we've been doing, I'll add 50 here. And because we took that 6 initial dollars, no matter what, everyone has to pay, plus our $2 times 50 people, we could just keep going depending on what we know. So 50 times 2 is 100, plus 6 is $106, is how much it would cost for 50 people. So that was the answer to number 3. And number 4 is really saying, is the relationship between the number of people and the total entrance cost a proportional relationship? Yes or no? Tell us how we know. And just like with that table, if you look back, every single scenario gave us a different per person rate, which is our constant of proportionality. And it was not the same every time, so it's not a proportional relationship. So you could write something along those lines. It's not a proportional relationship because the cost per person changes depending on how many people are in the van or in the vehicle. And that is how that situation goes. Sometimes it's drawing a table, continuing the table, drawing a picture helps. So if you need to do that to help you out, I would suggest that as well. All right, let's move on to the next problem, which is called running laps. And let me see here. So we don't have partners, so we're not going to do this with a partner. We're going to do this on our own or all together, you and I. What we've got here, and if you're looking on page 57, it says Han and Claire were running laps around the track. The coach recorded their times at laps 2, 4, 6, and 8. As you can see on both of the examples here, 2, 4, 6, and 8. And what we want to do is determine who's running the fastest. And we need to do our time. Give me just a moment. And we're going to say how many minutes per lap. So what I need to do is we think about the unit rate like before, minutes per lap, and we're going to do 4 minutes per 2 laps, which gives us 2 minutes per lap. I'm going to record this up above because remember this is my x and my y, and essentially I'm doing my y divided by x, which is our constant of proportionality. So I've got 4 divided by 2 equals 2 minutes per, I'm going to do MPL, minutes per lap. Let's continue. We've got 9 divided by 4 gives us 2.25 minutes per lap. We'll continue with 15 divided by 6, and that gives us 2.5 minutes per lap. And then lastly, we've got 23 divided by 8, which again, all of our y over x's, we're finding there, is he running at a constant speed? And we have 2.875 minutes per lap. Would you say that Han is running at a constant speed? He's not, because it looks like he actually, as time goes on, gets slower. And so he is not running at a constant speed. But let's take a look at our friend Claire. So for Claire, we've got, again, this is our x and this is our y. And our y over x will help us determine our constant of proportionality. And by y over x, I mean y divided by x. So I've got 5 divided by 2, which is 2.5. I've got 10 divided by 4, which is 2.5. I've got 15 divided by 6 when I type into my calculator. It's 2.5. And I would predict that if we type in 20 divided by 8, we also get 2.5, and we do. Now, what does this tell us about Claire? This tells us that Claire's speed, her minutes per lap, I'm just shortening it here, are the same as she runs along. So she runs at a constant pace. So what we can do is answer the question. So number 1 at the bottom asks about Han running at a constant pace, and we can say no, he does not. His times change every lap. And Claire, we know, is running at a constant rate. We know that she's running at a constant pace of 2.5 minutes per lap. And number 2 here, and I'm just going to write it at the bottom, it says, write an equation for the relationship between distance and time for anyone who's running a constant pace. So distance and time. So we could say that, give me just a moment. We could say that the time for Claire, for example, is the 2.5 times distance. Because if we had put t here, or distant, d, and it would be 2.5 d. And we know that our time is 2.5 d. So that's how we could say it for Claire's constant running, which is rather nice. So we will take a look now at reviewing our goal, which again was just taking a look at tables and determining if we have proportional relationships. In our first example, it was not a proportional relationship. Paying that $6 ahead of time really eliminated having a constant rate per person as we moved through. When we took a look at Han and Claire, we saw through Han's table that his constant changed every time, so he didn't have a proportional relationship. But Claire did. She ran 2.5 minutes per lap. So we determined that she did have a constant proportionality. Her relationship was proportional. Let's take a moment and do a couple of the practice problems. Let's take a look at number 1. Number 1 says decide whether each table could represent a proportional relationship. If the relationship could be proportional, what would the constant of proportionality be? Well, this is very similar to what we've done. I'm going to take a look, and with all of these tables, by the way, make sure you're on page 59. We'll take a look at x and y, and don't forget that our constant is y divided by the x. So what I like to do sometime is I'm just going to extend this table, and I'm going to put the constant right beside it. And I'm just going to type into my calculator. I know that I've got to do my y value, which is sound, divided by 5. So it says how loud is sound depending on how far away you are. Well, let's see if it's a constant sound wave here. So we have 85 divided by 5 equals 17. Let's type in another one. 79 divided by 10 is 7.9. 73 divided by 20 equals 3.65. Okay, and we've got 67 divided by 40 and 1.675. All of these have constants that are different. So what we've learned with Han's example, that if they're all different, it's not a proportional relationship. Let's take a look at the cost of fountain drinks at the hot dog hut. So I'm going to just continue it again. I just like keeping my information close by. So remember, this is going to be our y over x, our x, and our y. So let's try it. $1.49 divided by 16 is 0.09 and extending a little bit. Let's try again. $1.59 divided by 20. 0.079. $1.89 divided by 30. 0.063. Well, what do you notice about these two relationships? Did we have a constant proportionality on this one? No, it was not the same. It changed depending on how many ounces you had. Your cost was not dependent, directly related to it. So for this one, not proportional for A, not proportional for B. They tricked us. You assume, you think, well, one's gotta be, but nope, it is not. Let's go on to number 2. Number 2 is a little more complex. We'll talk this through a bit more. A taxi service charges $1 for the first tenth of a mile and then 10 cents for each additional tenth of a mile after that. What they want us to do is fill in the table depending on the amount based on this information. So we know for the first tenth of a mile, they charge us $1. And then for each additional tenth of a mile, we're paying 10 cents. So what I like to do is decompose these numbers, and I think it will help us sort of see the situation here. So if we look at 9 tenths, for example, I'm just going to write it here, 9 tenths. And I know that the first tenth out of there, we're paying $1. So I'm just going to kind of record it down below. Now, if I take 1/10 out of 9 tenths, I know that I've got 8 tenths remaining. And for each of those tenths, so I have 8 of them, I have to pay 10 cents. I'm saying a lot of tens here. So 10 cents times 8 becomes 80 cents. When I put these back together, I know that I am paying $1.80 for that trip. Let's take a look at the whole number 2. Now, the whole number 2, inside of it has a whole and 10 tenths more. I like to think of it that way. So if I take 1/10 out for my first $1, 2 wholes is the same as 20 tenths, because 10 tenths is 1 whole, so 20 tenths would be 2 wholes. So if I've taken 1/10 out of this, I just renamed it 20 tenths, I've got 19 tenths remaining. And I know that each of those tenths is 10 cents, a lot of tens again, but I know that I have 19 times that 10 cents. So that becomes $1.90. And then when I put these back together, I've got $2.90. I'm going to take a moment and erase one of these. And let's take a look at 3 1/10. Now it's pretty easy. We take 1/10 right out for our first $1. We have 3 wholes left over. And I know that there's 10 tenths in 1 whole, 20 tenths in 2 wholes, and 30 tenths in 3 wholes. The reason I put that in tenths as well is because we know I'm erasing again. All of the tenths are 10 cents, and I've got 30 of them. So that's $3. If you were to put that into your calculator, 30 times 0.1, you'd get $3. So we have here $4 as this expense. And I'm going to challenge you to do number 10 on your own. Let's take a look. And that is the end of the problems that I am doing with you. I'd like you to try on your own, finishing the problem we were just doing. Finishing on page 61, I'd like you to do number 3 and 4. And then if you turn to number 62, I'd like you to do number 5. So that's all for lesson 7 today. Please don't hesitate to reach out as always with any questions. I'm here to help and happy to help. Have a great day.